Thank you for inviting me and the opportunity to speak. I'd like to thank all the speakers who've gone before, especially because I took a very different view to Stefano's, which was that someone will have explained all the important stuff before I stand up, so I don't have to worry about that, more or less. So thank you for doing that. My abstract was a little bit tongue-in-cheek in the whole, the university is just mean and isn't producing anything for us. However, there is a serious point. So first of all, I should say, when I looked at the context of the meeting, I figured that the primary goal is to be giving information to people who are moving into this field. So if you've been working in multi-messenger astronomy for as long as I have, you're welcome to doze, because I'm not going to say anything that you probably don't already know. If you're new to the field, hopefully this will be interesting. But I also realized, terrifyingly, I know I've been doing TDAM since kind of like before it had a name. This is time domain and multi-messenger for those who haven't heard the acronym. But I've got this written down here. So I wrote my first gravitational wave follow-up paper in 2012, which was using data from 2009. I did my first neutrino follow-up in 2011, and I think this is just like a couple of years ago, and apparently it isn't. And I've actually been doing multi-messenger astronomy now for 80% of my career, which is horrible. And I have got one GWEM detection and one disputed GW neutrino detection EM neutrino detection to show for it. And so I'm tempted to say that my advice for you young people trying to come into the field is run for the hills. But I won't say that, because actually I think it's a field with huge potential. So this I'll go over fairly quickly because you've had a lot of the science around here already. I'm going to have to stop. I'm going to move this because I keep turning my face to the right and it moves me away from this microphone. Let's try putting it there. There we go. That's better. Okay, so I apologize to Dan and Alexis, who showed some really nice pictures in their slides, and I should have stolen those instead of one from other people. But this is just the kind of overview. So if we're looking for binary neutron star mergers to give us gravitational waves, as I hope you've picked up by now, we might be looking for jets, like my pointer's disappeared. So jets coming up and down here. Okay, fine. Something like this out at the top. Or possibly off-axis jets, if we happen to be looking out the side. We've heard a lot about off-axis jets, which really only became a kind of reality. People have been talking about structured jets for a long time, but it was only 1708-17 that gave us the data to do that. So this is a recent-ish paper by Gottlieb, by Ori Gottlieb, modeling the cocoons that you get as your jet plows through the medium and produces all this other stuff moving at different speeds around it. So if you're looking at the right angle, you might see some of what's coming down there. You should also get... So this is supposed to have a pointer that was working like 2 minutes ago. Ah, the pointer. Right, there we go. No, we don't. Go on, is it? Yeah, I've got a red dot on my screen, but it's not appearing on yours. Oh, never mind. Right, whatever. So I've lost my thread now. So yes, if you have the viewing angle right, you're probably not going to see a GRB. I mean, we'd love to. We sort of nearly did with 1708-17. We were really lucky. But if you get your angle right, you've got more chance of picking up this off-axis jet. And then as you go further off-axis, the kilonova emission starts to get in the way and block your view. But there are other bits and bobs like shock ejector you could get much later on in the radio. And of course, so your viewing angle very much affects what you see. In X-rays, we're really only interested in, well, the jet coming down the top, maybe slightly off-axis. In UV, we're interested, as you heard earlier in the week, especially in the stuff down the top and on very different timescales. Kilonova would be great. That's largely in UV from a Swift point of view and from an X-ray UV point of view, which is the context I'm talking in. So this is just a paper. This is the recent paper from Gottlieb, just giving a suggestion of an attempt to unify models in ways you might get different colors. The dominant factor here, for those who don't recall, is essentially what we call the electron fraction, which is a really useless name because we care about the fraction of neutrons, which is like the opposite of the electron fraction. But basically, the more neutrons you have in your outflow material, the further up the nucleosynthesis chain you get, and you end up with these elements that have just got loads and loads of valence slots open. And so there's like a gazillion different possible atomic transitions, and that just means you absorb everything, and you end up with this sort of infrared transient. If you don't manage to synthesize so much data, you have fewer neutrons, then actually you might only get to, say, nickel or beyond, and then or zinc or something, and then you get a much bluer kilonova. Or at least, you know, theoretically, this is all based on a relatively small amount of data. And something that is more, certainly from an X-ray point of view, but to me, quite exciting anyway, is the possibility of really nailing down magnetar spin down from one of these. When we had 1708-17, I was kind of hopeful that we might get evidence of a short-lived neutron star remnant. There would be a magnetar that would spin down. You get isotropic X-rays in principle from those. These are some models from Metzger and Pirro from more than 10 years ago. Crumbs, I'm getting old. But showing that actually you get potentially really bright, this is in luminosity, potentially really bright X-ray emission from this. So this is still a hope for off-axis. But on the other hand, it does mean that you need to have your magnetar live long enough to observe it with your X-ray telescope. If we go beyond binary neutron stars, we get to neutron star black hole mergers. As we've heard already just now, that the problem with these is that you might not get anything. It's a bit model dependent, but clearly there comes a point when if your mass ratio is big enough, you just swallow the neutron star whole. And if you don't tear it apart, you don't get any emission. Exactly where that boundary is depends on the equation of state and on the black hole spin, but probably once your black hole is above about 5 solar masses. And LIGO currently classify anything between 3 and 5 as a mass gap event. So if it's an NSBH as LIGO classify it, we're probably not going to see much. And then we've got binary black hole mergers, by which I mean stellar mass ones here. We've heard a lot about supermassive ones, but stellar mass ones, I mean, essentially, most models don't predict we're going to see something unless it happens to occur like in the disk of an AGN or something. But, you know, let's keep our options open. I mean, bear in mind that all of this is expectation. You actually only know what you're going to see when you've seen it. And we shouldn't build too many houses of cards on too little data. I was always taught that as an observer, our job is to make life tough for theorists. And, you know, I like to live by that. So, yes, okay, so that's the sort of things we're looking for. But as you've heard alluded to, how you look for them is an extraordinarily difficult challenge. So this is an event that doesn't get as much press nowadays because of old 170817 as I think it should. This is GW 150914, which occurred just before the LIGO 01 gravitational wave observing one started. And nobody, at least that I know, thought this was real. We thought this was a fake injection test by the LIGO community because it was right at the end of the engineering run and it was incredibly bright in terms of gravitational waves. And then it turned out that no, this was a genuine BBH. But the sky localization we're looking at here is well over 400 square degrees. These, by the way, this is a plot I make for Swift. So the sort of red box up here, my mouse has disappeared again. Okay, is it going to come back? No, whatever. The red box up there is where the bat field of view was. You'll be amazed how often bat manages to stare in the wrong direction. And the yellow is the 46 degrees around the sun that Swift can't point. And again, it's amazing how often that encompasses part of the GW region. I do have a little complex about the universe's attitude towards me, but honestly. Anyway, you don't have to search 400 square degrees. This is something we've known right from the start, even if we don't know what's actually going on, because it might, you know, you might have stuff that isn't mergers. There might be other things giving off gravitational waves. It's stuff, it's mass accelerating, and mass exists, generally speaking, in or near galaxies, right? That's something we do know about the universe. And in early LIGO days, the sensitivity was low enough that we knew where most, if not all, of the galaxies that could possibly have hosted an event were. So you could just look at those. It turns out that's still a heck of a lot. So Neil Gehrels, after whom Swift has since been renamed, Neil Gehrels proposed in 2016 with John Canizzo and Mansi Kasliwal this idea that galaxies are not all the same, obviously, but basically, if we assume that the probability that the mass of a galaxy is roughly related to its luminosity, which is probably fair enough in the infrared, and if we assume that the probability of hosting an event, a gravitational wave event, is simply proportional to the mass of the galaxy, then you can gain from the fact that some galaxies are bigger than others. And in actual fact, if you say we're only going to search the brightest 50% of the galaxy luminosity function, so we're going to accept that we're throwing away 50% of the probability, you have to search way less than 50% of the galaxies. So this is what these lines are kind of showing on here, is how many galaxies you have to search depending on the distance thing in order to get, 50% of the luminosity. And that's, quite a good and efficient approach, provided your galaxy catalogs are fairly complete. Although I suggested something else, which is actually and this tells you a lot about the kind of guy Neil was actually, that this is what we went with in the end. He didn't, despite being PI of the mission, he didn't dig in on his proposal. So the idea I said is, but equally, what if you've got 2 galaxies in this one field of view, for example, and what happens when you get to greater distances? So all we're really saying here is if you take a field of view, which is P for reasons that aren't very interesting, it's pixel, I think I had it, but if you pick a given field of view, the probability that the GW event is in a galaxy that we know about in that field of view is given by the probability it's in that position from the gravitational wave sky map, multiplied by the completeness of the galaxy catalogue, multiplied by some function that basically sums up all the galaxies along that line of sight, then says what's the probability it's at the same distance as the GW event, and then weights by luminosity. And then you have another factor which is becoming increasingly important, which is the probability that it is in an unknown galaxy along our line of sight. And that is basically given by the bottom term there, which is the gravitational wave probability multiplied by the incompleteness of the galaxy catalogue. So what we tend to do is take the gravitational wave sky map, we convolve it with this mass, and we get a sort of slightly smaller area to search. Turns out when I say smaller, so apologies again to Stefano from his earlier talk. He didn't like cumulative distribution plots, but I've got another one for you. But basically, this is just the sky area, the 90% probability sky area after galaxy convolution. And this is of triggers with a false alarm rate, quasi once a year or better. And I've thrown away all the subthreshold triggers we get now. They're not included in here. So basically, this is 100 square degrees, and it's about 10% of the events to date. Or let's take 3,000 square degrees, right, which is roughly the Einstein probe field of view in X-rays. Well, that's about half of them. Okay, so half of them, if the probability is all concentrated, which of course it isn't, then Einstein probe could in principle do it in one field of view. But this is still an extraordinary challenge, especially for stuff that you do from space, because we generally don't have as big a field of view or the ability to move around as quickly as on the ground. Although Swift can move pretty quickly, but it's got small fields of view. Okay, so those are the challenges. So let's just go through a bit of what we've seen and identify some of the other fun for the future. So it's not actually true that there's only been one binary neutron star trigger. There's been two, but I'll show you in a minute why no one talks about the other one. And we've heard a bit already this week about 230529, which I'll also show you about. So this is everyone's favorite event. So 170817. This was the original sky localization that we got from LIGO Virgo. And Virgo is really important here because without Virgo, we would not have got anywhere near this accuracy of position. And then this is what happens when we filter on galaxy catalogues. And you end up with a 90% enclosing area of less than a square degree. Here's my other piece of advice to early career researchers, which is never listen to anyone more senior than you. Because if we had just gone with what we've actually all agreed in advance to do, which was tile this in probability order, we would have got on target within a few hours. And I don't know if we'd have seen anything. We might have been too slow for the free we might have been too slow for the free neutrons and too quick for the kilonova, but still, you don't know if we weren't there. As it was, so there's a genuine problem. So first of all, Fermi also triggered on it, the subthreshold trigger, and the gravitational wave position was a long way from the Fermi center of the Fermi area region. The other thing, which if you weren't in the GW field at this time, you might not remember, but in 01 and 02, there was a tendency that when the gravitational wave localizations were updated some hours later, they kind of jumped a little bit to one side. I don't know if some of you remember that. And so someone who I won't name, but more senior than me at the time said, do we really trust? I don't think we should just select this handful of fields because I bet the position's going to move. Phil, can you just pad kind of around this a little bit? And it turns out that when you're sort of on a telecon, I can't remember what time of day it was, but it felt incredibly stressful, and they're saying we've got a ground station pass in 20 minutes, we need to get the plan done, then the only way I could come up to pad it out was an incredibly inefficient way, which meant that it was we didn't get there until after the sun had set and optical people had already discovered the kilonova. But even so, it turned out to be a fantastic event because it's not just about who gets there first. I mean, obviously, if we got there first, it's all about who gets there first, but we didn't. So, but these 6 people all independently discovered it, which again tells you the interest in the community. Here's the afterglow. It was found quite a lot later in X-rays. There was actually an X-ray non-detection with Chandra earlier than this. It was found in radios, as we've heard. For reasons that I'm not sure, the UV results didn't get put in the main Abbott paper, which is fine because it means I get to gratuitously cite myself. But we found it with UVOT. And this paper holds the distinction, at least for me, of being certainly by a long way the longest authorless paper I think I've ever been on and probably ever will again. Just kind of fun. And so I decided not to go through some of the results we got from that because you already heard, especially from Dan, about what you learned from these, the kilonova. We found from the UV that there had to be a fast-moving poloidal blue component to this, which had a relatively low electron fraction, and we can do some dynamic modeling and so on. But you've kind of heard about that, so I'm going to be talking about sort of the prospects, I suppose. I want to continue on to some other things instead. So this is the one you may have not heard about, GW 190425. And sort of part of the reason that you probably haven't heard about it is because it was really badly localized. And so even, there we go, even when you select only the galaxies inside it, this has a search area of nearly 4,000 square degrees. So we gallantly tried to follow this up with SWIFT with our 0.1 square degree field of view X-ray telescope and even smaller UV telescope. We did 407 fields covering a whopping great 6.5% of the probability. And strangely enough, we didn't find anything. What I will say, I haven't got this one because there was a trigger that was retracted, but there's a lot of work, and the guys at Penn State in particular at the Mission Operations Center did a lot of work on SWIFT to be able to maneuver the spacecraft loads and loads of times a day, to actually have this really short stare, quick move observations. We had an event in 2017 where we were testing this code, where we managed to observe 1,404 separate pointings with this telescope within 48 hours, which I think is pretty amazing for a spacecraft. And I know that there are new concepts that are using the same spacecraft body that are being proposed. So hopefully this kind of really fast slowing is still going to continue beyond SWIFT. So GW 230529, which we've heard about, this is this neutron star black hole trigger or mass gap or whatever you want to call it. So the masses are about 1.4 for the neutron star and 3.6 for the black hole. So it's a kind of interesting event. You know, what do we see when this happens? And now the answer is we didn't see very much at all. And a big part of the reason is the sky localization for that. I think you're going to be quite impressed with, because what we said was it was in the sky somewhere. You get four kind of nulls, which are, if I do my interferometer impression, there's a couple of lines you can work out where my arms have to move in sync with each other if I get gravitational waved. That's why we get these nulls. But basically, it could have been anywhere. But actually, oh, no, we can convolve with galaxies. Yeah, okay, doesn't help. So they're quite faint on there, but it's still basically everywhere, 12,545 square degrees. But have I got a slide falling out, or am I coming back to that? Okay, I've deleted the slide. I'm going to come back to that. It turns out you can still do some cool science with that, which I hope comes on the slide in a moment. I've forgotten what order I put these in. No, that was right. Yes, I want to stick with X-rays for a minute before I go into that. So there are still interesting things you can look at. Or actually challenges and horrifying challenges for the future that I want to get out of 170817. And this is my moment to tease Sylvia, because the first time I presented this was in Hanover. I've only presented these results twice at seminars in Hanover and here at Toulouse. And Sylvia invited me to give a seminar. And when I accepted, she then promptly left and moved to Berlin, which I think is quite an extreme way of saying I don't want to talk to you, but, you know, whatever. Anyway, this is the Chandra observation. So Chandra, there were lots of people who had access to who had Chandra proposals. There were 3 or 4 groups. So Nora was the first to publish. I was in Ryan's group. But this is the gravitational wave afterglow event thingy, right? And this is the host galaxy. And these are just other X-ray sources that by kind of bad fortune, the universe doesn't like me, happen to be nearby, right? And this, the scale here is 10 arc seconds. And 10 arc seconds on the point spread function of the Swift X-ray telescope or the Einstein probe, either of its telescopes, or the SWAM X-ray telescope, is horrifyingly small. And so this is my attempt to explain this. So this is the Chandra image where I've just smoothed it to with a kernel about the size of an XRT pixel. And this is what I thought we'd be able to do once we've got Chandra data. So what am I doing here? These 3 red things, these are the 3 Chandra sources here, right? These are all XRT data. This is the actual original XRT data. And what I'm thinking is, if we know where the Chandra sources are, let's assume that they are constant. We can take the Chandra positions and fluxes of these 3 things, convolve them with the XRT point spread function, and then put another source in at the position of the transient, which is this blue one here, convolve that with it as well, and then you fit that to the data, and you have 3 free parameters, right, which are a small x and y offset, because the way Swift works, its pointing is not, its astrometry is not perfect, and the brightness of the transient. And I tried this on, in total, 105 kiloseconds of data, and I think I managed at one point to get the the flux of the transient to go non-zero at about the 1.2 sigma level. Yay. But this is actually a real worry and something we need to be aware of, because this is only 40 megaparsecs away, right? So in other words, when we next detect a binary neutron star, this separation is going to get smaller. So it's not just that we need binary neutron stars. From an X-ray perspective, we'd like them in X-ray quiet galaxies as well, please, because it's getting, if it's on axis, gamma ray burst, great, fine, no problem, they're bright. But if we're not on axis, we're going to find it really hard to find the X-ray afterglow. Okay, right, that was it. I knew I was going to come back. I am going to come back to that other event in a minute. There are things we can do to help. So technically, this is maybe not quite X-ray. I'm going up to a bit higher energy, but shh, don't tell anyone. But the Swift BAT, so this is 15 to 150 keV. The Swift BAT is our burst alert telescope. It's what triggers on GRBs on Swift. However, the likelihood of a gamma ray burst and gravitational wave event going off, together on axis is pretty low. I mean, we were so lucky in one sense, actually, with 1708-17. I remember at the time people were saying that the line of sight to get this has got to be so precise. That can't be it. We can't be that lucky. Well, maybe the 8 years since have shown us how lucky we actually were. But even that, the detection with Fermi was sub-threshold. So Jimmy Delaunay and Sam Whaler and Jamie and Aaron Tohu have put together this really cool technique, which is called guano and nitrates, which are, they've got things they stand for, but it's to do with guano is bat dung, and we dump the bat data from Swift for certain things. So basically, bats, you can't normally keep the event data, but when we get a gravitational wave event trigger, we do keep the event data from bat. We dump it down to the ground, and they have this search called nitrates, which can look in a much more sensitive way than on board for any evidence of a gamma ray burst trigger. And these are just examples of places where they've, I think these ones are from their simulations, but where you get some actually really pretty accurate positions, potentially, if there's something that goes off. Okay. And so this is one event. It was a binary black hole. So this is GW 241125, so it's quite recent. And this is why I'm pretty sure, just in a minute, that my back position there is wrong, where the field of view is. Because with nitrates, they've actually found a subthreshold counterpart. It's probably not related. We never found a longer wavelength counterpart to it. So I say it's subthreshold. But it was 11 seconds post-merger. But you get a position here of 5 arc minutes, right, down from... Oh, I didn't have it written down, whatever it was on the last slide, many hundreds of square degrees. So if there is a kind of faintish gamma ray burst trigger like we had with 1708-17, this is a really good way of potentially recovering arc minute positions from it, as long as there is some kind of signal there. And of course, the back field of view is not huge. The thing I thought that I was going to show you earlier and forgot is this one. Even though we had essentially an all-sky localization for 230529, that's that black hole neutron star merger, that doesn't mean you can't do any science. Now, as it happened, between them, the Fermi GBM and the Swift BAT covered the entire sky, their fields of view did, which is fantastic. It doesn't happen as often as we'd like due to the way the orbits beat and so on. But there was no GRB detection down to about 10 to the 48 ergs per second, which is fainter than basically every GRB apart from 1708-17. So this actually placed, really, this is from Sam Whaler, Ron Keeney's paper, but this placed really stringent limits on the possibility of an on-axis gamma ray burst from this neutron star black hole trigger. So, not seeing something is not always a non-event. I know there are suggestions being made as well, it's difficult to implement, that say if you know that you don't have a gamma ray burst trigger, but you've got a gravitational wave error region, you could say, right, take the fields of view of the gamma ray burst satellites, and you don't exactly veto them because you could have an off-axis thing there, but in early times when what you're looking for is an afterglow, don't look at anywhere where a gamma ray satellite was looking, because we know there wasn't a GRB. So there's all sorts of cool stuff you can do with non-detections as well, which I think is going to pick up and move us forward quite a bit in the coming years. So that's a lot about the X-rays. Let me talk for a minute about UV, because what we realized with 1708-17, we hadn't really thought about the UV, we, as in the Swift team, about the UV emission, which is mainly because I was driving all this and I'm an X-ray person. But actually, now we've got a blue kilonova, we should think about more. So what my postdoc at the time, Rob Ailes-Ferris, did was he basically took a whole load of simulated mergers from the gravitational wave community and modeled they have inclination angles and everything, modeled both, okay, the kilonova and the afterglow emission using public models that I totally forgot to write down. Afterglow pi, which you've already heard about, and it's what's the one? MOSFET or something, is it? The kilonova is something, MOSFET? Sounds right. Yeah, there we go. And basically, ask the question, how likely are we to see these things with Swift? And how do you look? Because you've got this kind of problem that weighs against itself, that the longer you expose for, the more sensitive you are, so you can get a fainter thing. But if you've got to search 724 fields to get to the right place, then the longer you expose for, the longer you take to get there, and the thing is fainter. And how does that trade off? And so what I'm trying to show in this thing here, this is the area of the gravitational wave uncertainty. So there are 4 panels here for different exposure times. This is the distance of the gravitational wave event according to the gravitational wave alerts. And the colors going from blue, which means very few, up to red, which means all of them, tell you what fraction of events we would recover. And it's a little bit all over the place, but we end up saying it doesn't really matter so much what your exposure time is in about up to 250 seconds. But when you get regions bigger than 300 square degrees or more than about 300 megaparsecs away, at least with Swift, we haven't got a chance of detecting them. So at least that helps us inform what triggers we follow up, as if we've had those to choose from. But this is something that everyone has to think about, of course, with your own satellite or your own ground-based telescope. What do I follow up and how? So I'm not going to go through this, but this was a bit of fun. I have a Perl script that decides what Swift observes, and Sam Whaler has turned that into a nice flowchart, which I guess I should have done one day. So that's how Swift decides what it's going to follow up. I'm sure it's as clear as mud, but just to make the point, it isn't a trivial decision. But maybe you can do this a bit more generically, as I'll show you in a second. I just want to point out that I'm talking all about Swift, but we do now have Einstein Probe and SVOM up there. And SVOM has a visual telescope, which has not got a huge field of view, but it's got a 1 square degree X-ray telescope. And Einstein Probe has got like 3,500 square degrees worth of X-ray coverage. So these things actually are potential game changers if we get X-ray emission and if it outshines the host galaxy. And so we desperately need some triggers so we can find out if that's right. And they do that. I'm quite looking forward to seeing the first, well, any BNS, but the first BNS while these guys are up there taking data. So I just want to give this a plug as well on behalf of Leo Singer. But so what I've done for Swift is really kind of bespoke and put together for Swift. There's a mission coming called UVEX. It's going to be end of this decade, early next decade. It's a UV Explorer, which would be great for, therefore, searching for kilonova counterparts. But, you know, what Leo has found, Leo Singer, who's working on this, has found, as many of us have, that how to work out the optimal strategy to follow up is non-trivial. But apparently it has links to something called linear programming. And so if any of those words mean stuff to you, great. I've stolen them, well, he gave them. He straight off Leo Singer's slide. But the point is, he has this observation planning toolkit, which you can get on GitHub, which is designed to be multi-mission friendly to help you plan how is the optimal way for me to search a gravitational wave error region. So if you're interested, then do go and have a look at that, but don't ask me anything about it because I haven't a clue. So there we go. So my kind of take home is gravitational wave follow-up is really hard. I mean, we shouldn't. One day I'll stop beating myself up for what happened with 1708-17, but actually we should realize this is not an easy thing to do because the error regions are large. There are all sorts of challenges, but believe me, it's worth it. I think the best analogy I've ever been able to come up with is if you were a zoologist and sound didn't exist, right? And you spent years wondering why all those animals run away when lions open their mouths. Like, is it they've got really bad breath? Is it the size of their teeth? Whatever. And then one day somebody invents hearing and you could hear a roar. It would blow apart the way in which you did your science. And I think that this kind of orthogonal sort of measurement that we get from gravitational wave astronomy is the power to really change the way that we work. But we have to put the effort in, and there's a lot of theoretical predictions, there are a lot of models of kilonovae, and that's great, but we have to remember this is all based on very, very little data so far. That we have a number of kilonovae that have come up not from gravitational waves events, but we're still kind of, you know, I've got more fingers than we have kilonovae. But for those of you who are looking to move into the field, despite the fact that since 2017, goodness knows how many fellowship proposals have been funded, none of mine, for people to work on things that have had no detections for, it is a great time to work in the field. We've got SWIFT, we've got SWAN, we've got Einstein Probe. I mentioned UVEX is coming, CAGRA is gearing up, LIGO India will be joining. We've heard about ET and A Sharp and these things, but I'm not even looking that far in the future. We just need the university to give us some binary neutron star mergers. And I thought where I'd just end is when SWIFT was launched, pretty much every time we detected a gamma ray burst, someone would write a paper on it. And then there came a point where the editors said, guys, come on, we cannot just keep writing single burst GRB papers now. You've got to wait until there's something interesting or you need samples. And at the moment, we have almost the opposite thing. You know, the ratio of papers to events in the GWM community is huge, right? We've got so many papers out of this one event. I am looking forward. I really hope that I live to see the day that editors are saying to us, guys, you can't keep writing single event papers on GWEM detections. You've got to have something special about it to write it up. And I live in hope that that will happen. And for those of you who are just coming into the field and the young people who are starting out, you know, it's a goal and a time to aspire to, because I think, you know, the prospect is there. So I'll stop there and only take nice questions.
Thanks a lot. Thanks a lot, Phil. Questions? Yes. Sylvia wants to apologize.
Yeah, I assume so. No.
Yeah, I've always wondered this. So we, in general, right, target more luminous galaxies, and your explanation makes sense. But from the short GRB perspective, aren't they usually found in less exciting galaxies?
So yeah, this is a debate that's raged around a little bit. And forgive me, I've forgotten, there was a talk the other day because I made a note of this about the fact that in the nearby universe, you expect them to be more in the ellipticals, not with soft formations. Sorry, who was saying that? Thank you. Yes, exactly. And I was going to ask you, and then I didn't because I'm scared that I might have to change the way that I'm approaching things. But yeah, this is a difficulty. Certainly, we shouldn't be using star formation as a tracer. Although I think you also said, didn't you, that infrared luminosity is not a bad tracer for the map, yeah, as a whole, which is what we're using. There is a catalogue called Mangrove, which was put together by Jean-Grégoire Ducamp, who was at University of Paris, was one of the Paris universities, which is basically trying to get stellar mass into the galaxy catalogues and using that as a proxy, but it still kind of comes from luminosity. I don't know. I'm looking at some of the short GRB people. Do we have a strong feel of a bias towards galaxy types for short GRBs? I mean, they kind of occur in all galaxies, right? Yeah. Okay. Yeah. We know what to avoid.
Yeah. I mean, we know what to avoid in the sense that for sure we would avoid highly star forming stuff. We don't see them.
Yeah.
And I agree. What we say about star formation. So I think that maybe Paolo can comment as well, but I think I would wait more on mass than on star formation because we have we have example of short gamma burst of galaxies with ongoing star formation, but is very low as a star formation. So for sure we wait more mass than the star formation.
Yeah, I did some testing once, comparing what happened if I seeded in simulation, seeded events in galaxies by infrared luminosity, and then searched by blue luminosity, just to see what difference that would make. And it's not massive for something like SWIFT because I field of view is small, but it does make a distinguishable difference. So
I think that at the beginning there was a kind of misunderstanding in saying that, of course, those are events that are in some sense connected with star formation, but there is the delay to be taken into account.
Yes.
And so maybe there was too much emphasis to wait on this instead of
sure. I know I think there's a counterpoint. I'll just what was I going to say? I'll remember what I was going to say in a minute. Go on. What was I going to say?
No, it's just a comment on this to what Susanna said. Actually, two comments. One, the blue luminosity is not really a good tracer of star formation.
Okay,
so
sure.
It's not surprising that you didn't find much difference compared to the K band luminosity. And about the delay time, the point by Susanna is totally correct. And actually, I think that the community at the beginning was a bit too much of the idea that short delay times are more important than long delay time because there is this t to the -1 trend, which is probably completely correct, but t to the -1 means that you have a preference for short delay time, but you have also non-negligible fraction, like 50% of system with long delay time. And when you are at redshift 0, where star formation is not really effective, then all these long delay time systems form at cosmic noon, pile up, and you expect that their contribution to the merger system.
Sure. So would you encourage us, therefore, to target more, say, elliptical galaxies than, would you wait on galaxy type then, potentially?
Galaxies, well, I think mass is perfect.
Okay.
So K-band luminosity is perfect because it's more, in my plot, it was more the specific star formation rate.
Yeah.
So low specific star formation rate, which does not necessarily mean elliptical galaxies.
Sure. Yeah. I remember what I was going to say, actually, the other challenge to us here with targeting galaxies. So I put, when I didn't put this in this, when I do this, I add a halo of about 100 kiloparsecs around, but then think for, what's the number? GRB 23 thingy, the one with the kilonova that Andrew Levan and Gillian Rustinajad did recently. Can anyone remember the number? No. I can show, it's this what basically, I didn't put this in here because it's a GRB thing, but it's this, it looks like a long GRB, but it's got a kilonova. But the galaxy is here, and then the kilonova is kind of over here somewhere. And I can't remember offhand what the actual offset is in radially in kiloparsecs, sorry, not radially, transversely in like parsecs or whatever. But there is an issue that if you look at galaxies, the thing might have been kicked way out of its host galaxy as well. So, and especially if they've had long merger times, because if they've got a big kick, they've had a long time to be running at that speed. So there's a lot of difficulties.
But it's
It's fun. Yeah. Well, it's fun when we get triggers. Yeah.
Thanks a lot, Phil.
Okay.